Greetings from IIT Kharagpur. Welcome back to the course on physics of nanomaterials. Let us start the lectures of week 4 today. In the first 3 weeks, we have seen the importance of nanomaterials and nanotechnology in today's life. We have also seen that how to make nanomaterials. We have talked to you about a large number of techniques using which you can obtain nanomaterials. You may have also seen that there are techniques with different names, but the underlying principle using which the techniques are actually designed remain the same. You can also combine various techniques, call them as hybrid routes, and reach to a new protocol using which you can get functional nanomaterials or nanomaterials with newer properties. In almost all the lectures, at one point or the other, we were talking about the dimensionality effects and we were talking about the confinement of electron motion when the dimensions were being brought in the range of 1 to 100 nanometers. Owing to this confinement, you see a lot of variations in the physical properties as well as chemical properties. So, clearly electron motion is one of the first parameters which we should understand, and we will focus mainly on these topics in this week. So, let us start today's lecture, which is falling under the heading conduction electrons to electron tunneling. We will bridge week 3 and week 4 by introducing a novel technique by which patterning of nanostructures are now routinely carried out, and these patterned nanostructures show very interesting electron motion, electron tunneling, along with modulated conduction mechanisms. So, in today's lecture, I am going to talk to you about a top down approach which is called as lithography to obtain patterned structures. Lithography is basically coming in from two words, lithos and graphy. Lithos comes from the Greek word stone and graphy means graphically writing something. So, the whole concept is to design something on a given piece of substrate. So, that is where the word lithography is coming from. There are various types of lithography techniques which are available to us now. Each of them have advantages, and just like any other synthesis protocol which we discussed in the previous week, this also has limitations. So, we will see these aspects in today's lecture. Why is this term lithography becoming so important? This is becoming important because if you look into a structure, for example, I have taken these two scanning electron microscopes from two published literatures, and you can see that these are pattern structures which are from a film or a pattern which has been designed on a substrate. You can clearly see that the thickness can be tuned quite significantly in them. You can go from 60 nanometers to 250 nanometers to 300 nanometers. You can modulate the size, you can modulate the structures. For example, this modulates a pillar like structure with while this structure is showing you what? It is showing you a planar structure, sheet like structure. So, clearly some things which we thought when we were introducing the concept of nanomaterials, that you have a hair and you have to cut it down to very small sizes. So, if you cut vertically, a nano size hair would be the 1000 times lower piece than a normal hair size if you cut a hair which is in the range of micrometer thickness. So, but now you can see you can actually pattern these structures quite routinely, and I am using the word patterning, means they are well defined structures, there is no ambiguity in the design, they are well designed with equal spacing between the two. So, there is a gap. So, whatever you see would be a property of a single pillar like structure here. If you have a capacity to pattern electrode on one of them individually, then you can make circuits which are going to give you nano sized circuits. So, you can obtain such structures very easily nowadays. As I said, it is a top down approach. So, that means you have a substrate on which you have the material on which you want to obtain such kind of patterns, and then you perform certain steps that you finally reach to the desired pattern which is planned or aimed at the initial point of the work. This is routinely done using the technique lithography, and lithography is of various types. It is basically defined by the incident radiation which is used to modify the photoresist which is on the top of the substrate. So, you have photolithography, extreme UV lithography, you can have E-beam lithography, you have ion beam lithography, or you can have X-ray lithography. So, if I ask you what is photolithography? So, the incident beam would be a visible region wavelength. You will have E beam. So, it is an electron beam as the incident radiation. Ion beam, it is an ion beam which is acting as the incident radiation. You have X-ray as the incident radiation, or UV as the incident radiation. But the question immediately comes, incident where and for what? You are talking about fabricating a pattern structure, and then you are asking us to actually subclassify based on the incident radiation. These two concepts seemingly are quite independent to each other, but you will see why we classify the technique lithography into subheadings in subsequent slides now. So, basically the steps which are used to obtain a pattern structure means, for example, you are talking about a final structure which is given in figure G. So, this is what I want to obtain, and where have we started from? We have actually started from this structure. So, I have started from a structure and I have to obtain this structure which is the final structure. So, you have a substrate and on top of it is the quantum dot I am obtaining. So, let us understand the whole process and then we will go to more detail one by one. And we will talk about each aspects, like what is a photoresist, what types of photoresists are there, everything will be talked to you more in detail in subsequent slides. But before proceeding further, let us understand the whole process at one go. So, you have a substrate, step 1, on which you deposit the quantum well structure. So, you have a structure on which you deposit the material in which you want to get the final pattern structures. On top of it, then you deposit a photoresist. This is a resist which, when irradiated by the incident beam, changes its nature. So, the resistance changes at each and every point where the incident light actually falls. So, if you have a resist and the light falls in this region and not in the other regions, then this is the region where the resistance would be slightly different from that in the other two regions. So, this is what we are talking about. So, then you have it, then you use a shield or a shield which can prevent the light to pass through when you want to close the process. So, if there is an incident source, the beam is coming out, then you can use a shield in the middle, so that the beam cannot pass through and hit your quantum well structure which is mentioned here. But you have window in between. So, there is a window in between, so that there are certain regions in which the beam can pass through. So, when it passes through, clearly what will happen? The region in which they hit will change their resistance. So, what you do? Then you use a solvent or a dissolving agent which can dissolve the region which got irradiated by the incoming beam. So, now you have a photoresist and a region without photoresist. Clear? Now, what you do? Then you have the system where you add a mask. So, you use a mask and put it in the gap which was becoming available to you. Now, you have a system which is photoresist, mask and photoresist. Now, what you do? You remove the resist by using a developer or a any kind of a solvent which dissolves the photoresist. So, now you have actually removed these two parts. So, now these two parts are gone, but the mask is still there. Now, what you do? You have a system. So, if I can eliminate these two regions, then actually I may have a structure which is similar to what is required at the final point. So, this is what we are looking at. A single structure. So, what you do? Then you use a etching agent which etches out the sides and the material on the sides of the structure, that is the quantum dots which you require, and they are etched out. So, you use a etching agent and etch out the side materials which are not desired in the final structure. And finally, a mask. So, this etching mask which is there, a mask which prevents the region below it from getting etched out. Now, what I have to do? It is a mask. So, I can just remove the mask. So, if I remove this mask, what do I get? I get the final structure. So, this is a simple process by which you can obtain the desired structure. So, this is a single quantum dot which we talked about, but you can have a mask and you can have irradiation at different points, and then you can use a mask which is patterned mask, put it on top of the quantum well structures and then carry out these processes, and you will be able to obtain such kind of pattern structures. So, I hope you understand the basics of the lithographic technique. So, the same thing we can understand more in detail. So, you had the wafer substrate, you coated it with photoresist. One of the most commonly used photoresist is PMMA, polymethyl methacrylate. Then you expose it to light, then develop the pattern, etch out, that means etch out the exposed area, remove the photoresist, and you will get the patterns. Similarly, you can then talk in terms of metallization on the substrate by lift off. So, the same thing you can talk in terms of some kind of pattern metallization. Now, if you look into the whole process, we had talked to you about single structure, but you can carry out the same process if you have a photo mask with different patterns. So, you have different patterns. So, that means if you have the light falling on the mask and then you have the patterns below getting exposed, then the region will get exposed, the molecular weight will change, the resistance will change below. You can use a developer, remove those areas, fix it with mask, and then etch out the remainder materials which are not required, remove the final mask, etching mask, and you will get the patterns which you are looking for. So, you can make structures which are desired, and in India now you can have these masks designed as per as your requirement in many institutes. There are academic institutes which are making these masks and will be happy to provide to you, and there are also industries which can actually develop and design these masks and provide to the end user who wants to work in the field of photolithography. Now, when we talk about photoresist, there are two things which one has to be very clear about. The photoresist are of two types, means one is positive photoresist and other is negative photoresist. So, the positive photoresist become more soluble in a developer when exposed to light, while the negative photoresist becomes less soluble and remains as such after development. So, if you use positive photoresist, then the patterns which you will get would be just the opposite to what you will get by using negative photoresist. So, one is becoming hardened, other is becoming more soluble, and therefore, when you use a developer, the regions which will be removed from the resist would be just the opposite, and therefore, the patterns which you will get would be different in the different types of resist which you obtain. So, in photolithography, what is the incident beam which we are going to use? We are basically going to use some kind of optical beam as the incident and then carry out the whole process. So, you can have such techniques which can be used to obtain EICs or photonic integrated circuits. You can have MEMS or micro opto electron mechanical systems being made using these techniques. So, if you again look into the typical process, you have a substrate, then you spin coat, then you soft bake, so that there is a physical addition between the substrate and the top surface. You have the alignment of the mask, fixing of the mask and exposure to the light. Then you have post exposure baking, then you develop, post develop baking, and finally optical inspection to understand that you have obtained the material design which you were looking for. So, the lithography can actually be carried out in two modes. One is masked, where the exposure is through a mask, which we have been discussing till now. So, what is the advantage? It can give you simultaneous exposure over a large area, hence you have a high throughput, but the resolution is mainly limited by diffraction. You can have types of mask lithography. So, you have photolithography with mask aligners, you have photolithography with steppers and scanners, you have extreme UV lithography and X-ray lithography using this point. Then you have unmasked, where the exposure is without a mask. So, you do not use a mask, you just expose the surface by the beam. So, in this clearly the beam width has to be very small, otherwise the whole area will get exposed at one go, and then you are actually going to go back to the same quantum well structure with what you started with, because the moment you develop it, the whole photoresist will go. So, you have to have a very narrow beam width. So, you must have focused radiation beam, but now if I expose at one point, then I have to move the beam one by one to different points to expose the photoresist on top of it. Hence, the throughput becomes slightly lower than what you had in the previous case, and the resolution is mainly limited by radiation and radiation matter interactions. These unmasked techniques are being used in e-beam lithography, ion beam lithography and laser lithography, because here we can have very focused radiation beams. Now, if you now look into the resist properties. So, the major properties of the resin would be, you will have the solvents, the resin, the sensitizers and additives. So, what is there? The solvent gives the resist its flow characteristics. So, you have a solvent, because then when you coat it, spin coat it, you have to have it in a solution form, so that it uniformly coats. You dry it, and then the resist is physically added on the top of the structure. Now, resin is a mix of polymers used as binders, which gives the resist its mechanical and chemical properties. So, it is used as a binder, so that the resist is actually not inhomogeneously spreading. So, it binds the resist. Sensitizers, it is the photosensitive component of the resist material, and you have additives. These are chemicals that control specific aspects of the resist materials. So, the resist itself is a non-trivial component if you look more in detail. Let us then now see what will happen to extreme UV lithography. So, these are basically being used to obtain next generation microprocessors. These generally operate at a wavelength of around 13.4 nanometers, which are significantly shorter than deep UV lithography, and these are shorter, and hence they enable finer patterning. Generally, these radiation are obtained by exciting a stream of xenon gas using a high energy IR laser that produces a plasma which subsequently emits EUV photons. As no known material is transparent at 13.4 nanometers, therefore, conventional refractive optics cannot be used for EUV. The entire EUV optical systems, the entire systems relies on mirrors instead of lenses. So, it is basically relying on mirrors for manipulation and focusing. If you look into these mirrors, they are mostly made up of molybdenum and silicon or beryllium, which are engineered in a way that they have to reflect the 13.4 nanometer light. Similarly to optical lithography, EUV systems employ a 4x reduction projection system, relaxing the mask resolution requirements while still enabling high resolution patterning on the wafer. So, because of this process, you can obtain high resolution while patterning the structure on the wafer. Then comes the e-beam lithography. So, these are much shorter wavelengths than light. So, you have the source of e-beam, then you have the condenser lens, then you have the electron beam, which is now reaching the beam blanker, then you allow it to fall on the aperture. When the beam comes out of the aperture, you have the deflector, and then by this you can focus the beam. So, you can clearly see the beam is being focused on a very narrow region. So, you can use these condenser lenses and the aperture combinations to focus the beam, and then you can go on moving these beams from one point to the other. You can move the whole substrate in XY direction using a stepper motor at a rate which you think is optimum, and then you can get the desired exposure on top of the resist. The main drawback immediately you can see is it writes 1 pixel at a time, thus making it extremely slow for full chip writing. So, although quite precise, but it takes lot of time to carry out this process. So, when the electrons are emitted from the filament, they actually are accelerated. So, and then those are made to fall on the substrate. So, you can have various kind of emitters. You can have thermionic emission, you can have field emission, or you can have Schottky gun emissions of the electrons. So, when you have a field emission, you have a system which emits electron at only at high voltages, and therefore, you can go to very high energies of these electrons, and hence you can go to lower wavelengths. Now, you just have to replace electron beam with ion beam, and then the whole technique would be called as ion beam lithography. The concept remains the same. For example, in ion beam lithography, you use typically gallium ions or other heavy ions for pattern writing. It is how you can control the flow of these ions that becomes more critical than actually understanding the concept. So, if you have an ion which is moving through, then you have to have a more detailed understanding of the process by which ion flows is controlled, and then you can, once you have the capacity to focus the ion beam, you can carry out the patterning of nanostructures. Here mostly what you do, you use stencil mask, which actually complicates the lithography due to the difficulty in defining the intricate features. Now, based on the ion beam source, these techniques are actually then subclassified into two more. You have focused ion beam lithography, that is FIBL, and ion projection lithography. In FIBL, you are actually using, it is a process where you are using a serial maskless direct writing technique. Hence, you are using a focus beam to pattern the coated structure with a resolution of 5 to 10 nanometer. It is therefore mostly used for research, prototyping, and photomask repairing. But again, just like in electron beam lithography, this is limited by slow throughput. In IPL, you use a broad ion beam of, let us say, helium neon, and a stencil or scattering mask for parallel patterning on wafers. Hence, if you are using parallel patterning, the throughput becomes higher, but it faces the challenges like mask heating resulting in deformation, clogging of the stencils, and hence it limits its practical applications. Now, if you remove electron, you remove ion, then you can use X-rays, which are high energy X-rays, let us say coming out from a synchrotron source, and use that X-ray for exposing the resist to high energy beam, then you can undertake the same process which we have discussed till now, and you can obtain sub 30 nanometers features with the aspect ratios greater than 10:1 routinely by using these techniques. If you see and compare the advantages and limitations of these techniques, clearly you will see that none of them have only advantages or limitations associated to them. It is a combination of advantages and limitations which are associated to each one of them. For example, photolithography has high throughput, but you have limitation if you want to go to below 40 nanometers designs. E-beam has very high resolution, but you are looking at a process which is very slow. X-ray lithography has a very high resolution, let us say up to 30 nanometers, but it has a complex requirement of mask fabrication. So, depending upon the end user application and the quality of patterns in terms of precision, you have to choose the right process to get the desired nanostructures. So, these are some of the references which we have used today for taking the information that were shared with you, and I hope now you understand a very interesting and important technique of lithography using which you can have I hope now you understand the technique of lithography which is used to have high quality patterning of nanostructures on substrates, resulting in modulated electron flow and tuned confinement effects, resulting in newer physical properties in these structures. These structures, as we said, will have different electron conduction and tunneling properties, making them useful for next generation applications. So, in the next lecture we will start with these concepts. I thank you for attending lecture 1 of week 4.